What if you could count how many 1 bits are in the binary representation of every number from 0 to n, in just a split second? Counting bits is a Pattern Mastery 100 and LeetCode favorite because it tests if you really know how to optimize with dynamic programming and bitwise tricks. This problem pops up in Phong interviews and is a launchpad for mastering binary manipulation and efficient array filling. Ready to turn a brute force grind into a one-pass breeze? Let's get started. Let's break it down. You're given a number n. Your task is to return an array. Each position I in that array should tell you how many ones are in the binary form of the number I. For example, if n is 2, we look at the numbers 0, 1, and 2. 0 in binary is 0b0. It has 0 ones. 1 in binary is 0b1. It has 1 1. 2 in binary is 0b1 0. It also has 1 1. So the final array is 0, 1, 1. Now let's assess our options. A naive approach would use a helper function like bin I. Count 1 for each number from 0 to n. That works but is O(n) log n time. Can we do better? Yes, there's a dynamic programming trick. For any number I, the count of ones is 1 plus count of ones in I and I1. Or, using another pattern, count bits I equals count bits I right shift by 1 plus I and 1. That's because shifting I right by 1 drops the least significant bit, and I and 1 tells you if that dropped bit was a 1. This lets us fill the answer array in O(n) time. Here's the structure. Initialize an answer array of size n plus 1 with zeros, for every I from 1 to n. Use ens I equals ens I right shift by 1, plus I and 1, to fill in the value. Return the array. Let's try to implement it using solution 1. Alright, we're defining a function called countBits that takes one input, n. Our goal is to return an array where each position I stores how many ones are in the binary form of I. Here we create an array named res with length n plus 1, so it includes spots from 0 up to n. We fill it with zeros for now, like laying out n plus 1 empty boxes, all starting at 0. Now we loop from I equals 0 all the way up to n. We'll compute the bit count for each number one by one. Time complexity note: we do this for n plus 1 numbers, so this outer loop contributes the O(n) part. We set x equal to the current number I, because we're going to inspect it without changing I itself. And c starts at 0, this will be our counter for how many 1 bits we find. Now we keep looping as long as x isn't 0. This means we'll keep checking bits until we've shifted the number down to nothing. Since numbers here are treated as up to 32 bits, this loop runs at most 32 times, that's the b in O(n)b. This is the key bit trick. X and 1 checks the very last bit of x. If the last bit is 1, this returns 1. If it's 0, it returns 0. Then we add that result into C. Think of it like asking, is the rightmost light on? If yes, add 1 to the count. Now we shift x to the right by 1 bit. That's like moving to the next bit over, discarding the one we just checked. So we slowly peel the number down, bit by bit, until it becomes 0. This closes the while loop, meaning we're done counting all the ones in I's binary form. Now we store the final count C into res I. So the box at position I now holds the answer for number I. This closes the for loop. We've done the same counting process for every number from 0 to n. Quick complexity reminder: for each I we may scan up to b bits, max 32, so overall it's O(n)b, commonly treated as O(n) because 32 is fixed. Finally, we return the res array, the full list of bit count answers from 0 through n. And this finishes the function definition. And that's how this algorithm works. It first sets up an output array to hold results, then it loops through every number and counts its 1 bits by checking the last bit and shifting right until the number becomes 0. Efficient, simple, and elegant. Let's test our function using this input, n equals 2. This value represents the range from 0 up to 2, and we want to return an array where each index I stores the number of 1 bits in the binary form of I. Here's why the solution works. We loop through every number from 0 to n, and for each one, we count set bits by repeatedly checking the last bit with x and 1, then shifting right. For this input, 0 in binary is 0, it has 0 ones, res 0 equals 0. 1 in binary is 1, it has 1 1, res 1 equals 1. 2 in binary is 10, it has 1 1, res 2 equals 1. So the final array becomes 0 1 1. And that's exactly what our program outputs: 0 1 1. The code is working correctly and passes the test case. So, our implementation is correct. The algorithm successfully counts the number of set bits for every integer from 0 to 2 and stores them in an output array. Efficient and accurate. Now let's try another implement approach using solution 2. Here we define a function called countBits that takes a number n. Our goal is to return an array where each position I tells us how many ones are in the binary form of I, for every number from 0 up to n. Time complexity, O(n) because we loop through every number once. We create an array called res with size n plus 1, and we fill it with zeros. Why n plus 1? Because we want indexes from 0 to n included. And res 0, being 0 makes sense, 0 in binary has no ones. Now we loop from 1 up to n. Each loop calculates the number of 1 bits for I and stores it in res I. This is the key DP relation. We build today's answer using a smaller answer we already know. I1 means we shift I right by 1 bit, basically dividing by 2 and dropping the last bit. So res I1 is the number of ones in I without its last bit. In1 checks if I is odd or even. If the last bit is 1, this becomes 1. If the last bit is 0, it becomes 0. So we're saying, take the number of ones in the smaller version of I, and add 1 if I ends in a 1. That's why it's dynamic programming. We reuse work instead of recalculating from scratch. This closes the loop. By now, we've filled in res 1, all the way up to res n. Finally, we return the whole results array, the complete list of bit counts from 0 to n. And that's how this algorithm works. It first creates a results array pre-filled with zeros, then for each number it reuses the bit count from the number shifted right and adds 1 more if the last bit is set. Efficient, simple, and elegant. Let's test our function using this input, n equals 5. This value represents the range of numbers from 0 up to 5, and we want to build an output array where each index I stores the number of 1 bits in the binary form of I. Here's why the solution works. We reuse results we've already computed. For any number I, we take I1, that's I divided by 2, and we already know how many ones are in that smaller number. Then we add I and 1 to check whether I is odd, meaning it ends in a 1 bit. For example, I equals 1, 1 1 equals 0, and 1 and 1 equals 1 res 1 equals res 0 plus 1 equals 1. I equals 2, 2 1 equals 1, and 2 and 1 equals 0 res 2 equals res 1 plus 0 equals 1. I equals 3, 3 1 equals 1, and 3 and 1 equals 1 res 3 equals res 1 plus 1 equals 2. I equals 4, 4 1 equals 2, and 4 and 1 equals 0 res 4 equals res 2 plus 0 equals 1. I equals 5, 5 1 equals 2, and 5 and 1 equals 1 res 5 equals res 2 plus 1 equals 2. So we end up with 0, 1, 1, 2, 1, 2. And that's exactly what our program outputs, 0, 1, 1, 2, 1, 2. This confirms that our code is working correctly and passes the test case. So, our implementation is correct. The algorithm successfully counts the set bits for every integer from 0 to 5 using a fast reuse-based formula, efficient, accurate, and reliable. Let's wrap things up. This problem was all about counting bits efficiently, not just for one number, but for every number from 0 up to n. Breakdown recap. We started by understanding that for each number, we needed to figure out how many ones appear in its binary form. Essentially, we're building an array that shows the bit count for every integer in sequence. Assess recap. We compared two ideas, the brute force way using built-in binary counting, and a smarter dynamic programming method. The DP insight was that the count for any number I can be derived from smaller results, either by using I and I1 to remove a bit or by noticing that shifting I right gives us a related subproblem. This transforms a repetitive process into an ON solution. Structure recap. The plan was straightforward. Start from 0, and for each number, calculate its bit count using previously stored results. This lets us fill up the array step by step without recalculating from scratch. Implement recap. We coded this solution on LeetCode, and it executed smoothly without any syntax or runtime errors. Check recap. After running the test cases, the output matched perfectly across all inputs, confirming that our dynamic programming approach worked exactly as intended. The big takeaway? Bit manipulation and dynamic programming make a powerful combo. When you spot patterns that build on smaller subproblems, you can turn what seems like a heavy computation into something beautifully efficient.